Take a moment and imagine a large passenger airplane flying high above the clouds. Inside that aircraft are hundreds of passengers, luggage stored beneath the cabin floor, complex electronic systems guiding navigation across continents, and engines producing enormous thrust to keep everything moving forward at remarkable speed. But hidden inside one of the most unexpected parts of the airplane is something even heavier and more important than most people realize. Thousands of kilograms of fuel are stored inside the wings. At first glance, this sounds like a strange engineering decision. Wings look thin compared to the body of the aircraft. They flex during flight. They move slightly as air flows across their surfaces. And they do not appear to be the safest place to store something so heavy and so essential for the journey. It might seem more logical to place fuel inside the fuselage, where there is more space and where the structure appears stronger and better protected. But aircraft design rarely follows what seems obvious at first glance. Every major decision in aviation is based on precise engineering calculations, structural testing, and decades of experience gathered from thousands of flights. Storing fuel inside the wings is not simply a convenient solution. It is one of the most deliberate structural decisions engineers make when designing modern passenger airplanes. It is one of the most deliberate structural decisions engineers make when designing modern passenger aircraft. And it plays an important role in how airplanes remain stable and efficient throughout an entire journey. Welcome to Ordinary Things, Deep History, where we explore the hidden engineering logic behind everyday machines that quietly shape the modern world around us. Today we are going to explore why aircraft store fuel inside their wings instead of inside the fuselage, how this improves stability during flight, how fuel placement actually strengthens the aircraft structure itself, why some aircraft still include additional fuel tanks near the center of the fuselage, and how airplane tires survive the moment when hundreds of tons of aircraft weight suddenly meet the runway at speeds similar to a car traveling down a highway. When people first try to explain why aircraft store fuel in the wings, they usually give a simple answer. They say the fuselage is already full of passengers and cargo, so the wings are used as extra storage space. That explanation sounds reasonable, and to some extent it is true. Space inside the fuselage is extremely valuable because it directly affects how many passengers or how much cargo the aircraft can carry. Airlines depend on this space to operate efficiently and economically. But this explanation does not fully answer the question. If storing fuel were only about available space, engineers could place fuel tanks in many different parts of the aircraft structure. Fuel could be stored beneath the cabin floor, near the tail section, or inside specially designed compartments in the lower fuselage. Instead, engineers consistently choose the wings as the primary storage location. That tells us the real reason must be connected to something more important than convenience or available volume. The real reason begins with one of the most important concepts in aircraft design, something known as the center of gravity. Every aircraft must remain carefully balanced during flight. This balance determines how stable the aircraft feels in the air and how easily it can be controlled by the pilots. If the center of gravity moves too far forward, the aircraft becomes harder to rotate during takeoff and more difficult to control during flight. If it moves too far backward, it becomes less stable and more sensitive to disturbances in the airflow. Fuel plays a special role in this balancing problem because it is one of the heaviest components on board any large aircraft. Modern passenger airplanes often carry tens of tons of fuel at the start of a long journey. But unlike passengers or cargo, fuel is constantly being consumed as the engines operate. That means the aircraft becomes lighter during the entire flight, and more importantly, the distribution of that weight changes continuously from takeoff until landing. Engineers must carefully decide where this disappearing mass should be placed so that its consumption has the smallest possible effect on aircraft balance. The wings turn out to be the ideal location because they are positioned very close to the region where lift is generated. Lift is the upward force produced by the wings that keeps the aircraft in the air. By storing fuel near this lift-producing region, engineers ensure that the center of gravity changes only slightly as fuel is burned. This allows the aircraft to remain stable and predictable throughout the entire flight without requiring constant adjustments. There is another important reason why storing fuel inside the wings improves aircraft performance. And this reason becomes clear when we look at how forces act on the aircraft structure during flight. As the airplane moves through the air, Lift is generated along the entire span of each wing, pulling the wings upward. At the same time, the fuselage pulls downward because it carries passengers, cargo, and onboard equipment concentrated near the center of the aircraft. These opposite forces create bending stress where the wings connect to the fuselage, an area known as the wing root. This region experiences some of the highest structural loads anywhere on the aircraft. If the wings were empty, the bending force created by lift would be significantly greater. Over time, this would increase structural fatigue and reduce the lifespan of the aircraft. But when fuel is stored inside the wings, its weight acts as a counterbalance to lift. This reduces stress on the structure and helps protect the aircraft over thousands of flight cycles. In this way, fuel becomes part of the aircraft's structural support system rather than simply stored energy for the engines. Aircraft wings also already contain internal space that can be used for fuel storage without increasing the size of the airplane. Inside each wing are strong structural elements that maintain the wing's shape and strength. Between these components is unused internal volume. Engineers seal this space and allow the wing itself to function as a fuel container. This design is known as a wet wing system, and it allows large amounts of fuel to be carried without reducing passenger space inside the fuselage. Many aircraft also include an additional fuel tank near the center section of the fuselage. This tank is usually used during longer flights when extra fuel capacity is required. However, there is an important rule that controls how this fuel is used. If fuel is stored in the center tank, it is normally consumed first. This removes extra weight from the fuselage early in the flight and returns the aircraft to a configuration where most of the remaining fuel is stored inside the wings. Even the sequence in which fuel is used is carefully planned to maintain balance and structural efficiency throughout the journey. Sometimes aircraft must return to the airport shortly after takeoff because of unexpected technical situations. When this happens, pilots must consider another limitation known as maximum landing weight. Aircraft structures are designed with separate limits for takeoff and landing because landing places additional stress on the airframe. If the aircraft is too heavy to land safely, pilots must reduce weight before returning. They can remain airborne and burn fuel, or on aircraft equipped with special systems, they can release fuel safely at high altitude, where it disperses quickly into the atmosphere. Another impressive engineering challenge appears during landing itself. When a passenger aircraft approaches the runway, it may still be traveling at speeds close to 250 kilometers per hour. Yet all of that speed and weight must be absorbed safely by wheels that appear surprisingly small compared to the aircraft. One surprising detail about aircraft wheels is that they are not spinning before touchdown. While the aircraft is still in the air, the wheels remain almost completely stationary. The instant they touch the runway surface, they must accelerate from 0 speed to match the forward speed of the aircraft within a fraction of a second. This sudden acceleration creates intense friction between the rubber and the runway surface, which is why small clouds of smoke are often visible at the moment of landing. At the same time, the tires must support enormous weight. Large aircraft can weigh several hundred tons during landing. Instead of relying on only a few wheels, engineers distribute this weight across multiple landing gear assemblies so that each tire carries only part of the load. Aircraft tires are built very differently from car tires. They contain multiple layers of reinforced synthetic rubber combined with strong fibers and steel belts that allow them to support extremely high loads while absorbing landing impact forces. They also operate at much higher internal pressure than ordinary vehicle tires, which helps them maintain their strength under extreme conditions. Another important difference is the type of gas used inside aircraft tires. Unlike car tires, aircraft tires are filled with nitrogen instead of normal air. Nitrogen contains no moisture, which prevents freezing at high altitude. It also contains no oxygen, which slows chemical reactions that could weaken the tire over time. These properties make nitrogen safer and more reliable for aviation use. All of these engineering solutions work together to make something remarkable possible. Fuel stored inside the wings helps keep the aircraft balanced and structurally protected throughout the entire flight, while specially designed landing wheels absorb the enormous forces created during touchdown. So the next time you watch an airplane climbing into the sky or touching down on a runway, remember that many of the most important engineering decisions are hidden from view. Fuel inside the wings is not simply stored there because space is available. It is placed there to improve balance, reduce structural stress, and make flight safer and more efficient. Here on Ordinary Things Deep History, we explore the hidden logic behind the ordinary things that quietly support modern life every day. If you enjoy discovering how engineering decisions shape the world around us, make sure to subscribe and join us again for the next story hidden inside something you see all the time, but rarely stop to think about.